Okay, very well. So, good morning, class. We want to continue from where we left off um, last 2 weeks. Okay, we are looking at forecasting and production indices. Now, forecasting. When we talk about forecasting, what do we mean? We are saying that forecasting is needed, okay, in decision making, okay, and especially forecasting of agricultural production is very necessary for a lot of decisions at farmer level, at government level, business level, and so on and so forth. So what you say is besides farmers and dealers, public and private organizations dealing with agriculture are interested in providing the necessary storage and marketing facilities and for making available credit on the basis of what? Crop prospects. Okay, again, governments also require advanced knowledge of crops, okay, as crops are an important factor in national income estimation. Good. Now, let's move on. So we say forecast is an estimate of something which is yet to occur, or let's say having a knowledge of something in the future. Okay, it is defined as the most probable production of the crop, assuming, okay, factors such as the weather. Okay, we can also look at other factors like pests, diseases, which may affect the production. And when we talk about production, we mean the yield, okay, of various crops between the time of what forecasts and the final harvesting will be about the same as the average year. So we are saying that once we collect data, okay, on variables that can affect our yield, then we can run a forecast, hoping that our forecast will be the most likely, okay, production. In just basic terms, our forecast will be more or less like the yield we are expecting, okay? Then we are sure of the forecasting method or the forecasting tool that was employed in the forecasting. Now, there are various ways in which forecasting can be done. And an example is forecasting wheat production, okay? If we are forecasting wheat production, what factors can we look at? We can look at the labor force, we can look at lag output, we can look at the use of tractors, total rainfall, okay? We can even look at temperature. So there are so many factors that can come into consideration when predicting the yield of or forecasting the yield of crops. Now, as we have mentioned already, there are a number of beneficiaries when it comes to what forecasting crops. Some are the farmers, okay, who decide their asking prices, their inventory and marketing plans. Talk about traders, okay, for planning their logistic inventories and contracts. We talk about crop insurance companies. Okay, we talk about the banks. We also talk about exporters and importers, okay, making plans, okay, towards their contracts. Processing, we need to look at capacity, manpower, marketing strategy. Input, we look at production inventory, and so on and so forth. Government is also a prime beneficiary, okay, of efficient forecasting, which provides in advance a picture of economic well-being of the country. Okay, good. So these are all beneficiary and importance of what forecasting of agricultural production. Now let's move on. What do we require in forecasting? One, we need historical data. Okay, we need historical data to forecast, so we can easily forecast the next yield based on previous what data. And when we talk about that, we are referring to something like time series or regression. Okay, once we have data of predictors and what dependents from the past, we can always what predict what is going to happen in future. Then we also need historical data on factors affecting the data, okay, being forecasted. So these are predictors. So we need data on the predictors. The first one is data on what the output or the yield. And then second is data on predictors. And then finally, we need a better understanding of the historical data, okay? We need to understand the data itself, understand how things work or come to play in predicting the output before we proceed with the modeling. Good. Now, there are basically two main, let me say, categories of forecasting methods. We have the general quantitative forecasting techniques, and then we have the agro-meteorological forecasting techniques, okay? So when it comes to the quantitative techniques, we can look at several factors which affect yield. Okay, looking at the plants, the quality of soil, we can look at, general application of fertilizers, pests, and other issues. But when it comes to meteorological, we are limiting ourselves to weather conditions on the assumption that weather conditions such as weather, the rainfall, okay, temperature, and other weather patterns, okay, account for the production that we observe. And so these are the two main categorization. And we'll be looking at a practical example of one of these techniques, okay, in modeling agricultural yield. Yeah, so when it comes to quantitative tool, we have the reliance method, we have the causal method. Reliance methods make use of the time series analysis, trying to predict, okay, the yield based on previous years. Good. Whereas when we come to causal, we are looking at cause and effect relationship between what? The yield and other factors. Okay, good. So other factors including application of, how do we call it? The amount of fertilizer applied, the type of soil, the type of seed. We look at other parameters regarding even the crop itself, or we can even look at the labor that was involved, etc. Okay, how all of these things can account for what? The yield in causal methods. Now, when we look at the reliance methods, where we look at the time series, there are various methods, and you are all aware of time series. You know the models we can have. We can have the AR, the MA. We can have the ARMA, and then the integrated ARMA. Okay, models, which is the ARIMA models, and you all have practical knowledge of how to run what time series analysis or ARIMA models. Okay, using R, which you did last step. Okay, then we also come to meteorological. Meteorological, the key thing here is we are assuming that weather conditions are the main factor behind what short-term variations or interannual variations of the trended crop yield series. Okay, so here the underlying condition is weather conditions. Okay, good. And we can have the descriptive methods, we can have the regression methods. So the key differences here is when it comes to agro, we are looking at weather conditions as your independent variables, okay? But when you go to the regression in causal methods in the quantitative, we are looking at other factors aside what? Weather. You understand? Good. If there are any questions, you can raise your hand as I move along. So we know what descriptive methods are. We'll be looking at it in the practical sense. So let's move on a bit. So this is also an example of a regression method, okay, where yield is being estimated based on what? Rainfall and temperature. Okay, and we are saying that sometimes these um, models, okay, without sufficient knowledge, could have disadvantages or could be limited. Okay, so we say that the main disadvantages lie in the fact that they perform poorly outside the range of values for which they have been calibrated. Okay, so that is one main limitation with regression models. So given the set of variables that have been provided or the past data you have at hand, running a forecast with regression models sometimes are limited, okay, in terms of their predictability. Good. So our forecasts usually is more accurate within the scope of the data that has been provided. Okay, but beyond that, it becomes a challenge. So a typical example is this model is trying to tell us that we can, for example, this has a negative temperature in June and a positive effect in March. Okay, so let's say, for example, which means that if um, yeah, for example, if the temperature, if there's more rainfall in March, okay, then we are, and the temperature rises in June, then we are going to have, even though, let me put it this way, if there is even more rainfall in March and we get to June and the temperature goes very high, then we are very likely that the yield of crops is going to go down. That is what this model is telling us, because the coefficient of June temperature is 0.1, whilst the coefficient beta of March rainfall is 0.03. So June temperature seems to have more effect on the yield, a negative effect on the yield than the rainfall in March, okay? Which means that regardless of what happens in March and the months prior to June, once we get to June and the temperature is so high, then our yield is going to go down. But clearly, we know that around, okay, fine. So this thing comes down to practically, I mean, the practice on the field, okay? It will depend on when you planted a crop and when it is supposed to be yielding. But usually around June, we're expecting high levels of rainfall. So the interpretability also comes to play when we are modeling regression models. Yeah, so this is another typical example where of a regression model, causal model. This I picked from an article, okay, and it's trying to yield the production of wheat, okay, from based using other factors such as labor, number of tractors, fertilizers that were applied, and then the weighted average of rainfall for the year and for various months being factored in such a model, okay, to predict the yield. Now, another thing you realize in such a model is this time we don't have straightforward yield, okay? We don't have yield straightforward like that. You can see that the data has been transformed in a log, in a natural logarithm, okay? Which means that initially the data may have looked like that, okay? Upon prediction, you find out that our data sets are not looking, even for the scatter, we are not getting a very linear trend. So might be looking something like this, okay, or even going somehow like exponential, okay, good. So if they are going in an exponential manner, then one way to transform an exponential, okay, function into a linear function is to do a log transform of your dependent variable, okay, good, which we'll look at in the practical example if time permits us. Good. Okay, so let's go to a practical example. Now, before we go there, let me have some 1 or 2 questions if there are. So for um, the sake of revision, let me just touch on aspects of the modeling. Okay, we know regression is looking at what? The effect of independent variables on dependent variables. Okay, and it estimates what? The relationship between the independent and the dependent variable, where we look at the effect of the change in dependent variables as a result for changes in independent variable. That's the size of the relationship, okay, given by the beta. Then we look at the strength of the relationship. We look at the size, the direction of the relationship, and we also look at what the significance of such a relationship. That is all estimated using regression models. So let me move on. We have a lot of knowledge in regression analysis, but we clearly know these things. So for example, we have a relationship of X and Y, or multivariate, or what we call as multiple regression, X1, S2, S3. So usually when it comes to agricultural models, we look at what multiple regression, okay, analysis, and those are the relationships, okay, as outlined down there. Good. Let me skip this portion. Okay, we all know how to estimate a regression model, so let me skip that. Good. So basically, this is the estimated model which we use, okay, to predict, right, our output, okay. So our objective here is to estimate what? Our beta naught, okay, and then to also estimate our beta 1. Beta 1 is the coefficient, okay, of our X, and then beta naught is what? The Y intercept, okay. So, yeah, and to do that, we can estimate our beta naught, which in this case, okay, has been, so this is basically beta naught, and then this is our beta 1, okay, good. Now a typical example is indicated here. So in the formulas, we know how to conduct regression analysis. This is just a refresher. What you do is you just have to find the various components in the formula to get your beta naught. Okay, so just like we know, you find your beta 1 is estimated here, okay, from the data, and then your beta naught, which in this case has been written as A, okay, it's also estimated as 70.4, and then minus what? 0.28. Okay, so this is the forecasted model. So this is why estimate, okay, for prediction of what our yield in the context of our study. Now, so this is the analog or the manual computation, okay, for the regression best line of fit, okay. Now take note, we said beta naught is 70.4, beta 1 is what? Minus 0.8, sorry, 28. Now, when we go to our SPSS output, let's keep this for now. Oh, I think just a minute, please. So this is what we estimated earlier, and yeah, so these are output from the SPSS. So this SPSS output, okay, and clearly we can see, okay, the coefficient which we estimated earlier, that is given by the unstandardized coefficient as we see here. Okay, so this is the negative 0.0. 0.28, and then that is a constant, which is your beta naught, which is estimated here. Okay, then again, you can also find what the standardized coefficient, okay, by dividing by your standard error, okay, of the estimate. Good. Then another statistic we need, or let me say, let's look at all the statistics. The first statistics we're going to need is to look at the overall significance of what the factors, or let's say predictors in the model, okay, and that is usually given by your F statistic. Good. And for F statistic, it tests whether the coefficients are significant or not significant. Okay, good. So once you conduct this, you compare the values here. Okay, clearly it's telling us we have non-significance, okay, of coefficient, which is a bit of a problem. But we are not too much interested here for demonstration's sake. Then the next thing we look at is our R squared, okay, the R square value, okay, which gives us, that's the coefficient of determination. It tells us the amount of variation that is explained by what? Your predictor variables, okay? So amount of variation in your dependent variable. So if it is production of, let's say, corn, and you have selected two factors like temperature and rainfall, how much of the variability in your data, okay, in the corn yield data is predicted by your temperature and your rainfall, okay? If temperature and rainfall can predict more than 50% of the variability in the temperature, in the corn yield, then it means that your model has what? A good strength of prediction, okay? It is good for prediction. That is what basically it means. Then another method is, another statistic is the adjusted R squared, which is a better statistics than the R squared itself. Okay, and for all of these, our expected value should be 0.5, which is 50%. Okay, minimum should be 0.5. So adjusted R squared should be 0.5. So as it stands now, the model is telling us that our predictor is only able to predict, time is only able to predict about 27%, okay, of the variability in our output, okay, which is, I think this was medical data looking at blood pressure. Good. And that is not a good model, clearly. So already our F test, which is the ANOVA test, tells us that predictors are not significant. R square is telling us that the model is not a good fit, or model adequacy is not good. Then we talk about the coefficients here. Of course, we have the coefficients, but you also need to test the significance of the coefficients, okay? And that is done using the t-tests, okay? So you compare the p-values here. These are the p-values, okay? You compare the p-values with your alpha value, which is at 0.05, okay? And clearly, we can see that the p-value for our independent variable, which is time here, okay, 0.23, 0.213 is greater than what? A p-value, alpha value of 0.05, which is the default value used for the analysis, okay? Which, and we know that the test statistic, when we are testing for the significance of the model, is coefficient is equal to 0, or is not significant as against the coefficient is different from 0, okay? Good. And in this case, we do not reject the null hypothesis, meaning that the coefficient is not significant, okay? In very basic terms, what it means is it's better to have the data, just the data output, without modeling it using the time, because time is virtually irrelevant in predicting what our output, which is dBp. Okay, that is what it means. So this whole statistics is telling us that the model is not good for prediction. Okay, so that is how we interpret our results. And in exams, like I told you, I'm going to give you an output, and I'll expect you to be able to interpret the results, okay, in that direction and tell me what these things imply. Good. Now let's move on to a practical exam. If there is any question, you can bring it up. If there is any question, Crunchywa. Yes, Crunchywa.
Yeah, good morning.
Yeah, good morning.
Sir, please, the interpretation to the p-value and then the alpha value. Please, can you come again?
Yeah, anytime your p-value, anytime the p-value, okay, let me
hello, sir. Hello, sir.
Please, somebody is on the floor. Let me address that problem. So
As I'm adding small to the question.
Okay, go ahead.
Yes, sir. So please give us those points where we are going to report on and then explain them to us better, because I didn't get them well, as to how we can report on the modeling.
Okay, so that is exactly what I'm doing now.
Yes, sir.
P-value, okay, the moment it is less than your alpha value, we say that the test is significant. The test is significant. And usually the default, the default value for P, the alpha value is 0.05, means we test at 95% confidence, okay, CI. Okay, so any value that is less than 0.05 suggests that your test is being significant, okay? So let me touch on that again. Let's interpret the results we just saw. So for example, for the overall significance of your predictors, okay, p-value here is what? 0.213. 0.213 is bigger than 0.05. You understand? So this tells us that our coefficients are not significant. Okay, that is what it tells us. So overall, the predictors we've included in the model are not significant. That is what ANOVA is telling us. Good. Then the next place you'll be using the p-value is in the t-test. And the t-test, you always check the p-value of what? The predictor variable. So in this case, we have only one predictor, which is time. Okay, and the p-value here is 0.213, which is also greater than what? 0.05. Okay, so clearly that tells us that our beta, because the test statistic is your beta I is equal to 0 and beta I is not equal to 0. That is what you test, okay, in the t statistic. So your H naught is beta I is equal to 0, and then your H1 is, or the alternative hypothesis is beta I is not equal to 0. Okay, so if the test is not significant, in other words, you do not have evidence to reject the null hypothesis, then it means that you stick to the null hypothesis. If you stick to the null hypothesis, then what you are saying is beta 1 is equal to 0. Okay, but in our model, we said that Y estimate is equal to what? Beta naught plus what? Plus beta 1, okay, times. So in this case, the predictor is time, okay? So if you are saying that beta naught is equal to 0, And this is it. If you are saying beta naught is equal to 0, then what we mean is this whole thing, time is not important in predicting what your outcome, okay? Because the coefficient is 0. So 0 times time is 0. So it is not necessary in the prediction of what your output. So it's better you just make use of your outputs rather than running a regression model using time. Okay, so possibly you can go ahead and make use of a time series forecasting technique, because your data itself should be able to what predict itself. That is what it's trying to tell you. Okay. Yeah, so Kanchia's hand is still up. Okay, good. So let's proceed. We want to take a practical test, and um, uh, yeah. So this is data I obtained from few data, okay, on production, temperature, rainfall, and I also produce an interaction term here. Now, what we did is I've codified the rainfall and temperature to within a certain range, okay, and that can be clearly seen here. So I've put them into categories, temperature into categories, rainfall, temperature, and yield of maize. Okay. Now, per our past history, we know that maize grows at best in certain temperatures. Okay. From I think 19 degrees to around 20, 23, 24 degrees Celsius gives us the best yield. Okay. Or the best production. Good. So then we take various temperature. So we look at the temperature range from, we have some from 21 to 24, 25 to 28, 29 to 32, and so on and so forth. Then we also have the rainfall, average rainfall, okay, over the period, average rainfall over the period. Some will want to take it on monthly basis, but this one is over the entire period from various farms. That is about 21 farms, okay, or from 21 locations. Then after that also we have an interaction term. Now, the first thing you want to do when it comes to modeling in regression analysis, okay, is still regression. It's still regression. It's nothing different. The fact that we are doing agricultural stats does not mean hey, this regression is different. It's still regression. So you always need to find out the relationship between what your dependent, which is the yield, and then the predictors. Okay, and then see if there is a need, if it's a linear relationship. And if it's linear relation, then you proceed with your regression modeling. If not, then if there is need for data transformation, you have to transform the data. Good. So let's start with okay. Yes. So we have the child Buddha. I first have production in tons and then the rainfall. Okay. I've selected my scatter. I want a scatter plot of production. Let me just let me take the variables off and do them one by one for you to see it. So let me say I take it's been a bit slow. Yes. So then I'll select, this is my output, which is the yield. And then this is my predictor. So I put a predictor here. Okay. Which is the rainfall. And then I check to see the pattern of the data. I think it's even on the screen. Okay. So clearly we have what the pattern of production of maize and then rainfall. Okay, we can clearly see that this data is linear. Okay, it has a linear relationship, and with a positive slope, in the sense that when rainfall is increasing, production also what increases. We can clearly observe from the data. What about temperature? Let's go and see what is happening. Um, uh, okay, so let's take the graph for temperature as well. So all those conducting regression for your project work, okay, you need to begin with some descriptives and comment on the graph. Don't just jump in. And like I always say, ensure that I think I failed to record a part of the modeling. So let me go back and repeat that area. So like we said, you go to analyze, go to regression, we go to linear regression, and then you select your dependent variable, which is the production. We select independent, which are temperature and rainfall. Okay, and once we do that, we have options, we have plots, we have so if you want normality plots, you can plot the predictor against standardized predictors and the residual, and then select your normality plot. Then we can also look for, we can also save, okay, the standardized predicted and then the residuals. We can use the standardized predictors to also plot the normality, test the normality conditions of what our predicted values. Good. Now moving on, this statistic has already been computed here. And now before we comment on the model, like we said, you start from what? Your ANOVA table, okay? So the first thing is you check for the overall significance of predictors in the model. So this is the first one. You realize that p-value here is less than the alpha value of 0.05, 0.05, okay, which suggests to us that the predictors we've included in the model are relevant, they are significant. That's what it tells us. Then, okay, if they are relevant, what's next? Then we want to look at, okay, so what is the overall fit of the model? Or what is the overall adequacy? Or I want to put it in very simple words. To what extent do our predictors predict the variation in the outcome? Okay, and when we come here, we have 0.9, which is far bigger than 0.5. Okay, 0.9 means that we have about 98% prediction of what our yield, okay, being accounted by the two variables, temperature and rainfall. Okay, so which means that temperature and rainfall alone can account for the 98% of variation in the corn yield. And like we said, it's better to apply the adjusted R squared. Adjusted R squared is telling us we are still at 98%, which means that the model is a good model, and we should expect a model based on what? Temperature and rainfall. So this is our expectation that the corn yield is going to have some beta naught plus some beta 1, okay, temperature, and then some beta 2 rainfall. Okay, that is our expectation from the initial analysis we have here. Then what next? The next thing to do is let's go and check for the significance of beta 1 and beta naught. If they are not 0, okay, good. And when we come here, we have temperature is okay, 0.08, which is greater than 0.05, alpha level. Okay, alpha is 0.05, p is 0.08. So it tells us that this beta 1 is not significant. Beta 1 is equal to 0. And then when we come here, this is 0.00, which is less than 0.05. Okay, so it tells us that rainfall is very significant in predicting what our model. But you, like we said, you need knowledge in this thing. Clearly, we know that temperature is also relevant. We saw it from the descriptives that there was a linear regression, a linear pattern. Okay, and it seems to have a negative effect. Of course, negative effect, we know that we've seen that, and then it is also here in the standardized coefficient. We can see it's negative, just that it is not significant at a 95% confidence interval. Okay, so what do we do? The next thing you can do is to include an interaction term, because temperature is related to rainfall. So it's very possible that that is what is causing the non-significance over here. Okay, yeah, so we may want to include an interaction term and see whether the interaction term is going to be significant in this model. So let's go back and run with an interaction term, because we believe temperature should have an impact somewhere. Okay, but as it stands, it is not significant, and it could be because temperature is related to what rainfall. So we can run an interaction by adding interaction between temperature and rainfall. Let's do that. So we'll run that model. Okay, good. So once we include interaction, let's clear everything. You can clearly see that the model parameters have improved. Overall factors are significant. R squared has improved from 0.98 to 0.99. R squared, oh, sorry, from 0.98, yes, to it's still at 0.98, but this time 984. Adjusted R squared has also improved. And now let's go to the model significance and see. So this time around, the model we are looking at is this is the model we are expecting. Y estimate is equal to what? Beta naught. Okay, plus what? Beta 1 temperature. Let me represent that as T, plus beta 2 rainfall, and then plus beta 3 temperature times rainfall. Okay, so temperature times rainfall. That is the interaction term. Okay, and we are testing the coefficient of these three. So beta 1, beta 2, and beta 3. Those are the tests we are conducting, the T test. So when we come to the T test, these are those three variables. So for temperature, we realize that temperature is not significant. So coefficient here is 0. What about rainfall? Rainfall remains significant. This is significant in prediction. What of interaction term? Interaction term is also less than 0.05. So certainly the interaction between rainfall and temperature, okay, has an effect. So that is also what significant, which means that our resulting model, okay, will be what? Y estimate is going to be equal to, we have two, where is our beta naught? We have the constant, which is 1, 2, okay, 5, 37.762. Okay, plus our beta 2, which is for rainfall, which is 107.3.8 rainfall plus what? So this time it is a minus, so minus what? 11288179. Okay, T times the rate. Yeah, Sammy, your hand is up.
So for purpose of our project work, how do you calculate the interaction between the two predicting variables, the rainfall and the temperature?
Yeah, so
Hello, sir.
yeah,
Yes, sir.
I got you. Just relax. I'll come to that.
Yes, sir.
Yeah, so
Yes, sir.
this gives us the model, okay, which we require for prediction. So that is the regression model based on what meteorological factors. So this is one way of going about the modeling, which is this is purely quantitative and causal. Okay, good. Now, Sami asks, how do you calculate the interaction term? That is very simple. You go to data transform. So you can simply go to compute a variable here. And then interaction just means you are multiplying the two data. So it's temperature times rainfall gives you interaction. So you may want to create a variable called interaction 2. I already have interaction there, so I have interaction 2. Interaction 2 is going to be the temperature data, okay, times times what? Rainfall data. So that will give me interaction 2, and then you create, okay. So you've created your interaction. So next time you are running the analysis, you go to your regression. Then let me delete the initial interaction. This is your interaction 2 we just created. Add it and run the model, and you come to same conclusions. So that is how you create your interaction term. Now, what's next? The other way to go about the modeling, like I told you, will be to employ that is the reliance methods using your time series, okay, methods, okay. So we could have y at t is equal to some, okay, parameter plus what you can call it tau, okay, tau of this is just a coefficient of y at what t minus 1, okay, plus that is a time series model, okay, and that too we've done that. In fact, we've covered that extensively in class as at last term, okay. But to do that too, you need to start with the descriptives. You plot a series. Let's see the patterns in the series, okay, and the pattern will tell us what kind of analysis, whether it is stationary. If it is not stationary, you have to stationarize it by differential, finding what the difference, okay, the number of difference in the, and if you want to find the moving average or the AR techniques, you plot what your PCA, partial autocorrelation fancy and autocorrelation fancies to tell you which one are going to work. Then from there, you move on to your ARIMA model, okay, making use of those codes we gave to you in class. That should help you to be able to predict so easily for your project work. Okay. Now, so we have looked at methods of forecasting from a practical point of view, and we want to go back to class time. The next thing we want to touch on briefly before um, we bring down the curtains for today is to look at some index numbers or indices for agricultural production. Okay, how do we describe agricultural production? Okay, and measures of production. And in our country, we have measures like production PPI, which is the producer price index. We have CPIs, okay, and other production indices. Okay, good. Now, when we talk about an index, this simply means a statistic, okay, which is showing a measure of production. Okay, so in the case of our study, we are talking about production from year to year. Okay, and for measuring yearly changes, a base period is needed to help us to compare our measure. Okay, and we say that base period should be more than 1 year to absorb any abnormal fluctuations in the productions which may take place in 1 year, if 1 year is taken. Now, the third point will be more meaningful to us through an example. We are saying that merely adding up volumes of production of different categories of production commodities to measure production is not very meaningful. Okay, so if we just keep adding, let's assume we don't have CPI for food and non-food commodities in Ghana, we just keep adding production here, maybe yam production, cassava production, rice production, and we just put all quantities together. Do not really make sense. Okay, we need to go down and then assign a quantity which would take into consideration some weighting. So if we are talking about rice production based on what is the price of the rice. Yam production, what is the price of the yam? So that when we come out with an index which is looking at production, we would have factored in some kind of weighting system, okay, to really give it meaningful sense. There are so many types of indices. We have indexes of agricultural production. Index, when we say agricultural production, it includes food and non-foods. Okay, so things like rubber, timber and coal are not food, okay, but they are all in agriculture. We can have coupled agricultural productions and so on and so forth. So there are so many indices which cover, like in our context, we look at cereals, we look at tubers, we look at vegetables, we look at cash crops, indexes, and all that. So, good. Now, one measure is the quantum index, the production quantum index, which is not the best, because this one, it just compares quantity as against the quantity in the base period without factoring in any kind of adjustment or a weight. Okay, but the quantum index is just a quantity, the sum of quantity in, let's say, 2017 compared to the quantity produced in the base period, if it is 2000, then plus the sum of quantities in 2000, then we see the how do we call it, the amount of increase, okay, in percentage of production in 2070 as compared to that in 2008. Okay, and that is easily achievable here. So this time around, our base period is 2005, 2006. So if you just need what the quantum index, which is 124, you will divide this by the base period, which is 55547, okay, 0.2. Okay, so once you do that calculation, you should get 124.1. So it's just a matter of finding this divided by this, and that will give us, okay, the indexes, the quantum index for the various year. And if you need for food crops, okay, here we have for food, we have for fiber, we have other crops, okay, sugarcane. So if you need for food crops, you sum up what the quantum index that you have calculated, okay, for the various food items. Good. But we are saying that this is not a very good way, just putting together the total quantity that has been provided, okay, as an index is not the best way of doing that. So a more realistic approach to estimating our index, okay, a very good index is using weights. And what we mean by using weights, we talk about one very common technique, which is the last year's formula. Okay, that is what we use in Ghana here for estimating our CPIs and our PPI. Now, we're saying that there are many formulas used to calculate index of production. The most common one is the last year's formula. Okay, and the basic assumption here is that the price relatives fixed for the base period do not change for the whole period for which the index is computed. So this is the formula. We have what the price relative in the base year. This for base year. So when you see naught, this is the price in the base year. Okay, good. And then this is quantity in the base year. This quantity in base year. And then this is the quantity, current quantity. Okay, so this current quantity. Good. So it's just a summation of the quantity in the base year times the current, the price in the base year times the current quantity over the summation of what? The price in the base year times the base quantity. Now let's take an example to demonstrate the computation. Okay, so there's an example here. Let's just keep that. So we have we have the production in 1974, which is the current year. Okay, and the price in the base. This is price in the base year. I think it was 1967 or something. Okay, then these are also the quantities in the base year. So this is quantity in the base year, Q naught. Okay, so our last year's formula says what? We are looking at the price in the base year times the quantity, the current quantity, okay, over summation of what? The price in the base year times the quantity in the base year. Okay, so this will give us, so once you take the data here, let me just go back to the data